So we're going to be talking about recursion and the call stack. And that's I did want to use the whiteboard a little bit here and there. This is amazing, I have to say. I really do love like all the action. I'll keep poking around if anyone else, can also figure out. The challenge here is, as far as I know, what Zoom is telling me is if I share my screen, it closes the whiteboard for everyone, which is a real shame. But what I am going to do is now I'm scrolling up to the top of the whiteboard, but I'm guessing everyone is still seeing like the part where everyone's drawing.
Yeah.
Okay. Yeah. Let's see how we're going to do this. Can I just do a new one or? Oh, pages. Perfect. Okay, so if everyone could just maybe hold the drawing for a minute. We're just going to talk a little bit about a data structure called a stack. I can get. Oh, I don't even think my Apple Pencil will work. Yeah, I'm probably just going to switch. I'm just going to kill the whiteboard, to be honest. This is a little over ambitious, but it's a good starting point. We'll figure out the whiteboard. My Apple Pencil isn't even charged up, so I need to do a little more prep. The joys of technology. But I wanted to talk very briefly about a data structure called a stack. We'll learn more a bit about it later, and we'll see shortly why it's relevant. But I wanted, and can everyone see my screen right now? And does it have this image of a stack? Awesome.
Yes.
The reason that this is relevant is we're going to be talking about this a little bit with recursion momentarily. And this is exactly what it sounds like a stack of plates. This term LIFO, L-I-F-O, stands for last in, first out. We've seen arrays, we've seen lists. You can add something anywhere in a list and grab something from anywhere in a list. Same with arrays. You could use an array like we learned about yesterday to build a stack. Really, we could build a stack with anything. And in fact, you all will use like Python's like classes and stuff to build stacks. Really, tomorrow is when we talk about these data structures a bit more. But the basic idea is really straightforward. Imagine that, instead of a list where you append something to the end, you have maybe it's just called stack, and you do stack.push, and it puts something on the stack. And you can push a bunch of things, but the only way you can get something is with an operation called pop, and that always gets the thing at the top of the stack. So the concept is relatively straightforward. The application is a little less clear, and we'll kind of see what that is in a minute. But I just want to check in and see if this basic idea of what a stack is, without worrying about like how we would code it up too much or like why do we care, sort of makes sense. And one of like the kind of nifty things about a stack, let's see, I don't know if that calculator has an undo. It sort of does. It's like, where's a stack useful? Well, let's say I have a calculator, and in fact, let's can we view the tape? There we go. We got a little tape. 10 plus 5 times 5 minus 9 divided by 3. So, and the fun thing here is, I don't remember off the top of my head, there should be a button, really. I don't think this is an undo button, and I'm hoping I could demonstrate this easily. Maybe does the programmer's calculator have an undo button? This is kind of crazy, all this stuff. I actually didn't even know about this. So I can't really demo it as well as I wanted to, but if you all have probably used a calculator with an undo button, or even if you think about like a Google search, like, or just searching in the browser. Right, I'm clicking through some stuff. And now I hit the back button. So we've got this forward button. So this tells us that this history is something more like a list. But like, if we could only go back, if we could only undo, that's a good example of a stack, where you have a history and you pop. So this is it's a little abstract right now, and we're going to come back to it in just a moment. But like that's and in fact we're going to see it used in this way. And that's kind of like the classic use of a stack, is you have like a history and an order, and you can kind of move backwards. So now that I've tangented a little bit, let's talk about recursion, which will lead us coming back to stacks very shortly. And we've got this awesome sort of Winnie the Pooh infinite recursive GIF here. So recursion is like one of the fundamental ideas of computer science. And it's a technique often used when writing algorithms. And there are certain times when certain kinds of algorithms lend themselves to recursion, and other things don't. And just, it's a lot of fun. So I love throwing in, we've got some cool things here. And the easiest way to kind of demonstrate this is probably with a practical example, like factorial. So we saw this come up the other day. Remember, like big O of n exclamation point. So this is like the one, there's a couple bits of math that's sort of useful common programmer knowledge, and a factorial is one of them. Honestly, mainly because it might come up in programming interviews. The exclamation point we call factorial. So this is 1 factorial, 2 factorial, 3 factorial. So that's our factorial right there. And I think the diagram kind of makes it pretty clear sort of what a factorial is. 2 factorial is 2 times everything else that precedes it. So 1 and 2 factorial aren't that interesting. 3 factorial is kind of cool. 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1, which is 24. 5 factorial, 5 times 4 times 3 times 2 times 1, which is 120. So it gets very big, very fast, right? It gets big even faster, I think, than, right? We were looking at that big O chart. If this is our n, 1, 2, 3, like our list of size 1, size 2, size 3, well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So n factorial grows bigger much faster. So that's the basic idea of a factorial, and I just want to check in if people have any kind of questions around that. And there's a good chance that many of you have seen this, and if not, that's kind of why we wanted to just introduce it now. And I'm more than happy to chat a bit more about it later. So this is like sort of a classic programming problem to implement or to think about. And maybe how would we define this, right? This is a little bit more math, but not too much. N factorial is 5 times 5 minus 1 times 5 minus 2 times, and then this dot, 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 meaning basically everything else. You'll see this sometimes in sort of like math type proof language where it's sort of like once you see the pattern, we're just saying it continues onto 1. And this is great because now we have a way that we can maybe write a program to implement this. And does this notation up here kind of make sense to everyone? Cool. And I think I'll run this in a moment. And code it up, but just take a sec and we can look at this and we can see that, you know, it's pretty straightforward. We need a range, we have a result, and we're multiplying that result by the most recent thing. So, you know, we're going to have 5 times 4 times 3 times 2 times 1 and so on. And in fact, let's go ahead and run this. And I've got my slide deck up here, so I'm just sort of following it as guide code. So, you know, I obviously, because I know the code that I'm typing, I can move very quickly. And in fact, I'll just even for clarity, I'll just type it. That's not right. I'm gonna get confused if I do that. Someone actually maybe tell me, I think, what the right, I'm not sure if I got that right for the times equals, actually. If someone can tell me, that would be great. But I can go back and refactor it in a minute. Oh, in fact, I actually made a pretty significant typo. So well, it's not the point, but we can play spot the error in a moment. So I actually made a pretty big mistake here. Can anyone see what it is and point it out to me?
Line 5.
Totally. And Chad, thank you as well. I typed 1 instead of I. This red squiggly here was giving me a bit of a hint that I is unused. Now that should work. And now what I wanted to do makes a whole lot more sense. I got so confused, so I was like, result times 1, that doesn't seem right, but I didn't realize that I had typos. And let's go ahead and just run our factorials. So we've got our factorial program running. We've got a range. We do this bit of math. We calculate the factorial. Right, and kind of no sweat, so to speak. So recursion is about, let's actually look up the word. So the term goes back in math. And I don't know that much about it, but the key bit here is like the repeated application of a rule. This definition with computing is a little more confusing, related to involving a program where a part requires the application of the whole. Really like recursion, recurrence, repetition. There's an aspect of repetition, but there's also like an aspect of like something being defined in terms of itself. And that's sort of what this definition here shows. Like, we're defining a factorial in terms of itself. And it kind of works here, right? Because like 5 factorial, well, that's 5 times 4 times 3 times 2 times 1. Well, that's 5 times 4 factorial. And well, what's 4 factorial? That's 4 times 3 times 2 times 1, and so on. And in fact, let me just quickly do a little typing here in VS Code to sort of illustrate some of that. And let's just put it up here to make VS Code happy. Because I think once you see it, it helps it a lot to see it written out. And what does that become? That becomes five times 4 factorial, right? And what does that become? Well, a factorial is itself times itself minus 1 factorial. So 4 times 4 minus 1 factorial, which then becomes, and I think you all are starting to see where this is going a little bit. And 3 factorial, well, that is, let's see here. Well, I guess we don't need that there. It is 3 times, and I might be getting my parentheses wrong here, but I'm just going to do 2 factorial because I think you all start to see the pattern. And the important part of this definition, actually, that I missed here, that is sort of implied right here, and that we should have written down. And this is really common, both for sort of math proofs like this and recursion. 1 factorial equals 1. So at this point, I can kind of just get rid of my 1 and start multiplying stuff out. And in fact, I probably should have gotten rid of, I screwed up somewhere along the lines here with my parentheses. Because I think I have this factorial sort of like hanging out where it doesn't belong. Because the whole point is we sort of like brought it in. So this is a whole lot of parentheses, but it just then breaks down to, well, 2 times 1, that's just 2. 3 times 2 is 6. 4 times 6 is what, 24? And I don't need my parentheses here. I'll just get rid of them. And then 5 times 24 is 120. So I didn't quite write this out like, I think I probably made a couple typos along the way, but I do want to check in and get people's questions to see if this sort of makes sense and if this illustration helps, or what questions people have, or if people would like me to walk through a bit of this again to sort of see what's going on here and sort of how we're applying this recursive definition of a factorial. Oh, great question. What happens if it's zero? Excellent question. I'm 99% sure zero factorial is zero. In fact, I was wrong. Zero factorial equals one. And this pops up sometimes with math stuff, frankly. There is some logic behind this that makes sense. And actually, let's see if Quora. I'll just throw this in the Zoom link for anyone that's interested. But this is not uncommon either, where like for these sort of like recursive style definitions to work, sometimes we just need to be able to set stuff equal to one or deal with zero in a sensible way. Right? Because also zero factorial, it doesn't really make sense. Like you kind of want it to either be zero or one. And I think the problem with zero factorial being zero is, well, then one factorial equals one times, right? What if it's like this? Or, one time, like times zero factorial, and if zero factorial is zero, then we end up multiplying by zero and everything is zero. So I think that's kind of like the logic behind that, though that's like a very rough question. Yeah, great question. What other questions do people have, or things that are people curious about? And we're about to see how this translates into code. Okay, cool. So this is the fun part. I just wrote out that definition of a factorial in mathematical notation, more or less. We can do the same thing by writing a little program, right? An algorithm, some Python source code. We can call a function inside the function itself. And that is a little confusing, I know. I think the one thing to think about is like we talked about like lookup tables very briefly yesterday, where I said like, hey, if I like create a var X, like when the Python interpreter, that Python program runs and reads this code and it sees this, somewhere it stores this value 5 in memory and stores somewhere, hey, like if I'm asked for like what the value of X is, go grab this value of memory. It has a little lookup table of our key, which is the name of this variable and its value. And it does something similar with functions. When we define this function, like the Python interpreter, it probably doesn't like literally save this text. It probably does some work to it. But in essence, the definition of this function is stored somewhere in memory that our running program is using. And then when our program stops running, then it's deleted. But so that's why, and I think I'll just type this out in VS Code in a moment. That's kind of digging into the weeds a bit of how this works, that this is defined in terms of itself. Like Python notes this down, but it also, the interpreter kind of knows, like if it's reading a function and then it says this, it doesn't create definitions over and over and over. I think, when you write like a language runtime or a compiler, you have to like write in a little logic to handle like what to do with recursion, basically. And in fact, let's go ahead and just type this out and run it. So because it's always, I think, easy to talk about it when we have it as code. So I'm just going to put a little R in front here for recursive. And Matt, I see your question about each function creating a new layer on the stack, on the call stack. And yes, that's exactly where we're going in just a minute. And I know that this week there's a lot of stuff we're throwing at you, and this stuff, it does, the reason it connects to Big O is that often, like, we'll be looking at recursive algorithms and want to figure out their runtime complexity. And we might do a little bit of that this week, but that's sort of the connection between these things. And in fact, it wants a function or method docstring, and in fact, we can give it that recursive factorial. In fact, I will just grab these rules here, and we can just put them there. And that's the beauty of the Python docstring. These three double quotes are what's called a docstring, which lets you make a multi-line comment. And one of my plugins is encouraging me to do best practice, which is to always have a docstring for at the top of every file and for every function. And it is a great habit because it does make life easier in terms of code readability. And I'm not sure what these little, oh, it looks like I have some trailing white space. I'm not going to worry about those little blue squigglies. And let's go ahead and run this stuff again and make sure that my program works. Right, so I'm not doing total test-driven development here, but I am running my code, and I have some good answers, so I know what to expect. And lo and behold, I do get the same answers, so this does work, which is great. And now, but yeah, what's up?
Don't you need to rename the functions because you're running the old function?
Oh, yes, Megan, thank you so much. I absolutely do need to do that. Sorry, I didn't mean to interrupt you. You totally hit you. Yes, absolutely. My brain was getting a little too excited there. Yeah, I'm so glad you mentioned that. That's one of the classic categories of programmer error, by the way, is like I'm copying and pasting and moving my code around, and then I forget I need to rename something relatively simple. Great call. And the worst kind of error, because I was like, oh, everything looks correct. I think it's good. But lo and behold, I didn't realize that I hadn't renamed this function. There's something to be said for typing stuff out. So we've taken this same definition that we wrote down in math of recursively defining a factorial, and we've just turned it into a program. The 0 factorial, we don't directly have to worry about because when we hit 1, we return 1. So this keeps us from ever getting to 0. And there's a special name for this. When we're writing a recursive algorithm, the bit that returns stuff and does no more recursion, that doesn't call our function again recursively, is called the base case, because you can think of it as the base or the bottom, right? The base case, like if n equals 1, we are done recursing, we return 1, that's our base case. And if we didn't have this base case, you know, what happens when I run this program? Let's see, we didn't get to see this printed out, but this error message does kind of illustrate my point. If, by the way, reading error messages usually what you want is at the bottom of the error message, and then what you see is like sort of the stack trace moving up. Sometimes you have to look at the top of the error message. Note that the top of the error message does tell us the line where this issue occurred. It says, hey, on line 53, we made this function call and that caused us problem. And then we actually have a trace back, right? Saying, hey, I ran this code, I called this, executed this line on line 53, and that caused the problem. And here's what it did. So 53, they basically trace it through to line 50. They don't worry about the function definition. And that is in fact the only bit of logic I have inside this function. So it's basically saying, hey, line 53 then executed this code on line 50, read it, hit it on line 50. There's this fascinating statement here, previous line repeated 996 more times. So it ran this line a whole lot, and we had recursion error, maximum recursion depth exceeded. And in fact, if I print out, in fact, it'd be kind of fun to put this at the top of this anyway. Print f string n is n. Now we can watch this print out a bit, and it should really go after the dot string. Let's see, do I have a typo? I don't think I have a typo. I think it just didn't print it out because the recursion depth got exceeded.
I think it was there if you scroll up.
Oh, it was. Oh yeah, there we go. So also, I mean, first of all, without that one, this is like recursion gone wrong. Like we've gone into negative numbers, and a factorial should never go into a negative number. I wasn't printing my sum or my product rather. So n is a little less interesting actually. I should have printed out the product as well. But you sort of get the idea of why this base case is so important when we're writing recursive algorithms. It's sort of like if you have a while loop, but your logic is messed up and it goes on forever. Fu, just one moment, sir. And so the one thing I want to quickly point out about this error message is this statement right here at the bottom, recursion error, maximum recursion depth exceeded while calling a Python object. So, sort of like I was saying, recursion, I apologize. I don't know if y'all can hear it. There's a motorcycle outside my apartment. Recursion is like a core computer science concept that pretty much every programming language I can think of has. However, it has to be sort of explicitly implemented in, right, the runtime, the interpreter, the compiler, the thing that looks at our source code and turns it into ones and zeros for the computer to actually run. And there have to be some rules around it because otherwise it can go on forever. And so whatever group of people wrote the Python interpreter, decided the maximum recursion depth that's allowed before we just stop things. And Fu, yes, sir. And thank you for being patient.
Did you put the entire recursive inside the if and else statement?
Say that again.
Do you put your return statement inside the else statement? If and else statement?
Great.
Like if the base equal to 1, and then you else return the n factorial.
Great question. We do not need an else statement here. I could do an else, and it would look like this. And the program should work the same way. And in fact, let's run it to make sure that I haven't lost my mind. It does. I'm just getting a lot of these annoying, that print statement is a bit of a double-edged sword there. So we can add an else statement and our program will work the same way. The reason I don't need an else statement here is because inside this if statement, we return. So if n equals 1, we return, and then we never get to here because our function has returned. And so that's why we don't need the else statement. Like if we're doing something else here, like say, I don't know, x equals x plus 3 or whatever, then we might indeed need that else statement if we only want, this return to happen when we don't do this. But because inside our if statement we return, that means the function returns, execution doesn't continue, and we don't get here. So we don't need the else statement. And this is a pretty common pattern that you'll see. Sometimes it's called a guard. But essentially, if you've got like a return statement inside an if, you might not need like an else. Does that make sense? And if I didn't explain that well, that's okay. You guys will see this pattern a lot more. And again, there was no harm in having the else here. So if you're in doubt, feel more than free to just put in an else where you feel like it should be. And as you continue to write code and get feedback, we'll point it out and comment it. But since when this is true, we return, our code never gets to here, so I don't need the else. And this way I can just write my code a little cleaner and the else statement is unnecessary. Yeah, great question. What other questions do people have, or what else are people curious about?
Hey, Adam, I was looking at the lecture. Looks like maybe you're gonna get more into the details of this. I don't want to get ahead of it, but I just don't understand. Like, I don't understand. Like, I don't grasp the concept of how it all actually works.
Yeah, let's keep on rolling and see if that helps a bit, Matt. And I think recursion is one of the more sort of complicated concepts in computer science. It's sort of like deceptively simple. And that's part of why we want to introduce it in the class. And I'll move that comment out of the way so we can sort of see this a bit more easily. So the key thing to remember here is like, when I run my Python program, Python kind of looks through everything before it starts executing code, and it's kind of saving this somewhere. And then when I call it, Python says, cool, let's call this factorial R function and pass in my argument. And, I pass in 5 as an input, and it says n is not 5. All right, awesome. We get to here, do 5 times. Oh, I need to call it again. Let's call it again and pass in 4. And does this and says, hey, this is in 4. What do I do now? Well, I do 4 times. Oh, shoot, I have to call it again. Let's call 3. And I'll go through it in the slide deck in a moment. But the same way, sort of writing out, we had 5 minus 1 factorial, and we can replace that with 4 factorial. And then by using this definition, we just literally replace, right? It looks a little scarier than it is. Really, all that's happening here is we replace 4 factorial with 4 times 4 minus 1 factorial. And we'll worry about this later. And that's kind of exactly what's happening with a recursive function. But let's kind of step through that and see what that looks like. And just as a brief sort of comparison, for these sort of like imperative or iterative is the term, like the step-by-step implementation, we use like loops and conditionals, if else statements, right, and variables and stuff. With recursive, we really need that base case, right? This thing that says, this is when we stop, we don't want to recurse. The part where we recurse is called the recursive case. And we use this return statement to sort of like bundle up our solution. And so, Matt, I think I'll kind of get to what you're asking in a moment. I do just want to walk through a bit more of what we have here. and we might be due for a break soon, in fact. Let's see where we are. Let's actually see what a good stopping point is. Yeah, I think this is a good stopping point right after this. So after the break, we'll look at how recursion is kind of like implemented. Josh, great question about big O for the factorial function. I don't remember off the top of my head. It might be big O of n factorial, but I'm honestly not certain. But kind of coming back to this, so we'll worry about the implementation in a minute. But a recursive algorithm has two parts: a base case, this second one here, and you usually want to often you define this first, and this is sort of the special case that like causes us to stop, right? Something that doesn't recurse, that doesn't call itself again, where it's not, we're not incepting like another level down, so to speak. We've also got to define our recursive case. And again, think about the factorial, right? 5 factorial is the same as 5 times 4 factorial. So this is a good example of our recursive case, the part that we can sort of like define in terms of itself, where we do want to incept. And then we need to use return statements to build up these recursive steps so something is finally returned. And that's what we're going to learn about after the break. And we're going to talk a bit about the call stack, which is like a core part of pretty much every programming language, and I think pretty much every computer. Maybe there's something really exotic out there that doesn't have one. And that is a stack, just like we learned about. But now it's probably a good time for a break. I'm looking at the questions. I see people answering questions. I think that the big O of that recursive algorithm that we wrote of defining the factorial, it probably is big O of n off the top of my head. Yeah, that would make sense. I think it is big O of n, because if I'm looking at this, the important step here is like recursing. And how many times do we do this? We basically do this n times. Like for a factorial of 5, I am calling myself, it's 4 times, but that's basically 5. That's basically n. And in fact, we could use, like, to test this out, if we wanted to, we could have we could have that print statement of just printing n. Oh, excuse me, I had a cough there. And I'm pretty sure that would show us, if I comment these guys out. Yeah, our function is calling itself 5 times. And in fact, I think this is a good last thing to do before our break. A great way to kind of learn and understand algorithms is lots of print statements. Let's see if this helps at all. This is what we're going to do after the break, but oh, I forgot to close my parentheses there. We're going to see this with a bit more clarity after the break, but this is the first time our function calls. Here, I'll bring this. Actually, what I'll do is And we will bring you. Oh, there's some way to do it, but that'll work actually. I just wanted to sort of be able to get stuff clear, and we'll run it again. Perfect. Okay, I need stuff to be visual. So right, our program runs, it calls our function, and is 5, and is not 1. We jump over here, we're about to recurse. We hit return, but the return statement, we don't need parentheses here, but sort of for purposes of explanation, I'll put them in. Because the thing to think about is, you know, many of you may have written something like this at some point. The return statement doesn't return 3. It returns the sum of this, right? If I stick a bunch of stuff over here, or like, I don't know, right? If I have more code in here, when the Python runtime is reading through this, it says return, what do I return? Then it says, oh, I have more work to do. I got to figure out what this stuff is, get that value, and feed it back to return. So you can almost, if you want, think of return as its own little function that we can put stuff into. The same way that here, when I call this print function, I call another function and do this, and this doesn't try to print out like this function definition or the word factorial. The Python runtime goes inside the print statement and says, hey, I have more work to do. I have to figure this out and then feed this back to the print statement. And so that's exactly what's going on here. Python hits this line and says, hey, I return, what do I return? N, well, N is 5, that works for me. But what is this? I don't know. Oh shoot, I have to call this function again. And pass it 4. And so we can see that that kind of repeats each time until finally we're calling this, you know, we're passing 2 minus 1, we hit this base case, we actually return 1, and then 1 is returned back to, like, each of these return statements kind of cascades. So like 1 is returned, and then we can see here it's like 2 times 1. We'll get into this after the break, actually, because we have some good visual aids in the slide deck, and I actually want to use the debugger. So this is probably a good time for a break, though. Why don't we take 15 so we can all stretch and properly like refresh our brains, and then we'll come back and we'll kind of like walk through this again. Sound good? Awesome. And I hope
Hey, Adam, just wanted to, oh,
Yeah.
sorry.
no what's
Just
up?
wanted to say I was here.
Oh, awesome. Much
Just saying
appreciated.
here. Yeah, okay.
Thank you. And Matt, I hope that helped a little bit. Yeah, Clarice, thank you for letting me know. Anyone else who's here who wasn't here earlier, just ping me, and I'll see everyone in 15 minutes. Cool. Thank you, everyone.